Section 1.4, Definition of Derivative. Southwestern College, Professor Maria Olivas. Definition of derivative. Objectives. Define the derivative in the context of a slope function. Determine when a function is not differentiable. Let's begin by drawing a picture. I'm going to draw a coordinate plane. I'm going to draw the y-axis and the x-axis. I'm going to label the x-axis with an x, and I'm going to label the y-axis with f of x. I'm going to draw an increasing function, and this increasing function is going to be concave up. I'm going to label the function with y equals f of x. Let me begin here by first writing out the formula for slope. Slope is equal to m, and m is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And this is going to be equal to, I'm going to write this as delta y over delta x. That's going to represent the change in y's over the change in x's. Now I'm going to go ahead and I'm going to plot a couple of points on my function. I'm going to begin here with this point that I've plotted. I've plotted the point in quadrant 1. I'm drawing a dashed line segment down from my point to the x-axis, and I'm labeling that x value with an x. I'm drawing a horizontal dashed line segment from the point to the y-axis, and I'm going to label that y value as f of x. I'm going to plot another point further to the right on this function. So I'm going to draw the point right about here. And now I'm going to draw a dashed vertical line segment going down from my point to the x-axis. And that value of x, I'm going to label it as x plus h. Now I'm going to draw a horizontal dashed line segment from that point over to the y-axis, and I'm going to label this y value here as f of x plus h. I'm going to go ahead and label each one of these points with its corresponding ordered pair. That first point that I drew, that's going to be x comma f of x, and the second point will be x plus h comma f of x plus h. I'm going to draw a secant line that goes through both of those points that I drew. I'm going to draw this line in blue, and I'm going to draw an arrow pointing to the line. I'm going to write secant line next to it. And also next to it, I'm going to write m subscript secant to represent the slope of the secant line. And that's going to be set equal to f of x plus h minus f of x over h. Now I'm going to draw a line that is tangent at x equal to x. This is going to be drawn as a red line, and I'm going to label this line as the tangent line. So I'm going to draw an arrow pointing to this line. I'm going to write down the words tangent line next to the arrow that I just drew. And I'm going to write the slope of this tangent line. So I'm going to label this slope as m, and then I'm going to put subscript tangent to the m. So m tangent. And then I'm going to set this equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So the slope of this red tangent line at x equal to x is our derivative. This is our geometric representation to help you visualize what a derivative is. And I've also written next to that red tangent line, the m subscript tangent is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And that is also the way that we represent the derivative using limits. and using the difference quotient also. All right, moving on. The slope of the secant line on f between x and x plus h is going to be, I'm going to write this as m subscript secant, and this is going to be equal to our difference quotient, f of x plus h minus f of x all over h. This is the average rate of change for f on the closed interval x to x plus h. I'm going to go ahead and just lasso my difference quotient that I wrote here, and I'm going to shrink it and bring it down, just lower it a little bit, and so it looks a little more centered, and box that in. Okay, so going back here, let's write this in. This is the average rate of change for f on the interval, on the closed interval from x to x plus h. Next, the slope of the tangent line on f at x is going to be what we wrote up above earlier. It's going to be, I'm going to write this as m subscript tangent to represent the slope of the tangent line, is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is going to be representing the instantaneous rate of change. I've gone ahead and put a box around that with the slope of the tangent line, how it's represented here as a limit. And we're writing in now, this is the instantaneous rate of change for f at x. This is given a special name as well. We call this the derivative of f. And we have a lot of different types of notation to represent a derivative. So I'm going to go ahead and write some of those different notations down right now. So different ways we can represent the derivative, given that y is equal to f of x, would be, I'm going to draw an arrow here pointing to the right, and now on the right hand side of this arrow I'm going to write the different representations that we can use to represent the derivative. We can write it as the derivative of f of x, and sometimes we call this also f prime of x. We can write this as the derivative of y, or y prime. We can write this as dy over dx. We can also write it as dx of f of x, which basically means the derivative with respect to x of f of x. I'm just going to go ahead and lasso in those different types of notation for the derivative that I wrote. I'm going to move it slightly to the left so that it looks a little more centered. Okay, now we're going to write down the general form. So the general form of a derivative is going to be f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So that is going to represent the derivative of f of x. So this is very important to memorize. So right here, it might be a good idea to write down the word memorize so that we all remember that this has got to be memorized. Next, to find the instantaneous rate of change, or in other words, the derivative, we need to compute this limit, either in general or at a specific x value. Steps to computing this limit. 1. Write the difference quotient. What is the difference quotient? Well, let me tell you. The difference quotient is going to be equal to this. First, let me write out the words difference quotient. And then I'm going to say this is equal to f of x plus h minus f of x over h. Step 2, simplify the difference quotient. And then step 3, find the limit as h approaches 0. And once again, the limit that you're looking for is going to be that definition that we gave for derivative. So it's going to be the limit as h approaches 0 of the difference quotient, which is f of x plus h minus f of x over h. Example 1. Find the slope of the function, that is, the derivative of f of x equals 3x minus 4 at any point x comma f of x. So I'm going to begin by writing f prime of x, or the derivative of f of x, is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So I'm going to write f of x plus h is equal to 3 times the quantity x plus h minus 4. Now that I know what f of x plus h is equal to, I can simplify it. So I'm going to distribute that 3, and I'm going to get 3x plus 3h minus 4. Now going back to the limit that I had written earlier from the definition of derivative, I'm going to set that equal to the limit as h approaches 0 of 3x plus 3h minus 4 minus the quantity 3x minus 4 all over h. And this equals the limit as h approaches 0 of 3x plus 3h minus 4 minus 3x plus 4 all over h. I can combine like terms, so the 3x minus the 3x, those are going to cancel out. So I've highlighted those and I've marked those off with a red line. And the negative 4 and the positive 4, I've highlighted those in green, and I've marked those off with a red line to show that those cancel out. We will be left with the limit as h approaches 0 of 3h over h. We have a common factor of h here in the numerator and denominator, so I can divide those out, and I'll just be left with factors of 1. And I'll just end up with the limit as h approaches 0 of 3. And this is going to be equal to 3. So I'm just going to go ahead and rewrite here. The derivative of f of x equals 3, and I'm going to box that entire thing in. And I'm also going to write this out in words. I went ahead and wrote the derivative of f of x equals 3. Or another way we could say this, we can say f prime of x equals 3. So now we are ready to move on to example number 2. Example 2. Given f of x equals x squared, find the derivative of f of x, then find the derivative of f of 3. Step 1. Find f of x plus h. F of x is equal to x squared. So therefore, f of x plus h equals x plus h quantity squared, which is equal to x plus h times x plus h, which equals x squared plus 2xh plus h squared. Step 2. Use the limit definition of derivative. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. I'm going to highlight the f of x plus h, and I'm going to highlight what f of x plus h is equal to up here, the x squared plus 2xh plus h squared. And the f of x was equal to x squared, so I'm going to highlight the f of x in green, and I'm going to highlight the x squared in green. I'm going to substitute now. F prime of x is equal to the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared over h. I've highlighted the x squareds in blue, and I have canceled them out by drawing little red lines through them to show that they zero each other out when we add them up. This is going to be equal to the limit as h approaches 0 of 2xh plus h squared over h. And this equals the limit as h approaches 0 of, I can factor out the h, and that'll give me h times the quantity 2x plus h over h. I can divide out the h's, so I'll be left with factors of 1 in their place. And then this will be equal to the limit as h approaches 0 of the quantity 2x plus h. I can now do direct substitution. So this is going to be equal to 2x plus 0, which is equal to 2x. So f prime of x, or the derivative of f of x, is equal to 2x. So I found the first part of what I was being asked to find, so I'm going to box that in for my first answer. Now it's asking for f prime of 3, so f prime of 3 is going to be equal to 2 times 3, which is equal to 6. So f prime of 3 equals 6. I'm going to go ahead and box that in. And I've answered all the parts to this problem. Example 3a. Find the slope of the function f of x equals 3x squared minus 2x plus 1 at any point x comma f of x. So first I'm going to start off by highlighting the entire problem in yellow. And then I'm going to have an arrow pointing upwards, and I'm going to write in here, in other words, find the derivative. So many times here when we're doing these problems, it's kind of hard to figure out what exactly is the problem asking of us. If it's asking us to find the slope of a function, it basically wants us to find the derivative. So I'm going to start off by finding f of x plus h, which is going to be equal to 3 times the quantity x plus h, quantity squared, minus 2 times the quantity x plus h, and then plus 1. So f of x plus h is equal to, I'm going to try to simplify this as much as I can. I'm going to have 3 times the trinomial x squared plus 2xh plus h squared, and then we have minus 2 times the binomial x plus h, and we have plus 1. F of x plus h is equal to, I'm going to distribute the 3 to each one of the terms of that trinomial, so it'll give me 3x squared plus 6xh plus 3h squared, and then I'm going to distribute that negative 2 to the binomial, so I'll have minus 2x minus 2h, and then we have the plus 1 at the end. So f prime of x is going to be equal to the limit as h approaches 0 of, I'm going to write f of x plus h minus f of x over h. This is going to be equal to the limit as h approaches 0 of, I'm going to draw out a big fraction bar, and in the numerator I'm going to write 3x squared plus 6xh plus 3h squared minus 2x minus 2h plus 1. And then I'm going to subtract f of x, which is inside parentheses, I'm going to write the trinomial 3x squared minus 2x plus 1. I'm going to go ahead and lasso everything that I wrote here for f prime of x, and I'm going to shrink it a little bit and raise it and move it slightly towards the left so I have a little bit more space. And then underneath that last fraction that I was writing, I'm going to write an h in the denominator. I'm also going to show that I'm going to distribute this negative in front of the trinomial, so I'm going to draw arrows towards each one of the terms in the trinomial to show that I'm going to distribute that negative sign. F prime of x is equal to the limit as h approaches 0 of, I'm going to draw a big fraction bar, and now in the numerator I'm going to write 3x squared plus 6xh plus 3h squared minus 2x minus 2h plus 1 minus 3x squared plus 2x minus 1 all over h. I'm going to highlight the like terms. So I'm going to highlight the 3x squared and then minus 3x squared in yellow, and then draw red lines through them, canceling them out. And now I'm going to highlight the negative or the minus 2x and the positive 2x in green, and I'm going to draw red lines through them, canceling them out. And now I'm going to highlight the positive 1 and the negative 1 in blue, and I'm going to draw red lines through those two, canceling those out. F prime of x is equal to the limit as h approaches 0 of, so I'm going to have left over in that numerator 6xh plus 3h squared minus 2h all over h. Since each one of the terms in this numerator has an h, I'm going to factor out that h. So this is going to equal the limit as h approaches 0 of, I'm going to write h, open up a set of parentheses, 6x plus 3h minus 2, close the parentheses. This is going to be all over h. I can cancel out now the factors of h that I have here in the numerator and denominator, and I'm going to write 1s right next to those h's since they divided out, and I'm just left with factors of 1. F prime of x is equal to the limit as h approaches 0 of, inside parentheses, I'm going to write 6x plus 3h minus 2. Now, I can go ahead and do direct substitution. I'm going to substitute 0 for h, so this is going to be equal to 6x plus 3 times 0 minus 2, which is equal to 6x minus 2. So f prime of x equals 6x minus 2, and I'm just going to go ahead and box that in. That's going to be our answer for part A. Part B says, now find the slope of the tangent line at x equal to 3. So in order to find the slope of the tangent line at x equal to 3, I'm going to take the equation that I have for my derivative, and I'm going to substitute 3 for x. So f prime of x is equal to 6x minus 2, so I'm going to rewrite that equation down. And now I'm going to write f prime of 3, and I'm going to substitute 3 for x, so it'll be 6 times 3 minus 2, which is going to give me 18 minus 2, which is equal to 16. So that 16 represents the slope of the tangent line at x equal to 3. So our slope is equal to 16. I'm going to box that in. C. Write the equation of the tangent line at that point. So the equation of the tangent line at that point, I need two things to write the equation of a line. I need the slope and I need a point. So I have the slope. I just found that the slope is equal to 16. And I know the x value, or the x coordinate of my point, is going to be equal to 3. So I just need that y value. I know that my equation is f of x equal to 3x squared minus 2x plus 1. So if I substitute x equal to 3 into that original function, I should be able to get my y coordinate of my point. F of 3 is going to be equal to 3 times 3 squared minus 2 times 3 plus 1. Let's simplify this. So this is going to give me f of 3 is equal to 3 times 9 minus 2 times 3 plus 1. And now this is going to be equal to, I'm going to write this below now, f of 3 equals 3 times 9 is 27 minus 2 times 3 is 6 plus 1 is going to be equal to 22. So f of 3 equals 22, or in other words, my point is 3, 22. Now that I have my point and I have my slope, I can go ahead and find my equation. I'm going to erase the slope that I had written earlier and the original function I had written up above here to make more space. I'm going to write down point slope form. Y minus y sub 1 equals m times the quantity x minus x sub 1. And I'm going to write x sub 1 and y sub 1 right underneath my ordered pair. So I'm going to have y minus 22 equals 16 times the quantity x minus 3. I can go ahead and simplify this, or I could box this in, right? Because this technically is the equation already. So I'm just going to go ahead and box that in, and that's going to be the point slope form of the equation that I have found here. If I wanted to write this in slope intercept form, let me rewrite the equation here. I'm going to distribute the 16, so I'm going to have y minus 22 equals 16x minus 48. I'm going to add 22 to both sides, and I'm going to get y equals 16x minus 26. I'm going to put a cloud around that, and that equation represents my answer in slope-intercept form. All right, for part D, it says repeat parts B and C for the tangent line at x equal to -1. Or I'm going to just erase the part that said slope-intercept form, and I'm just going to shrink the work that I did for the slope-intercept form, and I'm going to raise it a little bit so I have more space to do part D. F prime of -1 is going to be equal to 6 times -1 minus 2, which is equal to -6 minus 2, which equals -8. This is equal to m, my slope. F of -1, now I use the original equation, that's going to be equal to 3 times -1 squared minus 2 times -1 plus 1. So f of -1 is going to be equal to 3 times 1 minus 2 times -1 plus 1. And f of -1 equals 3 plus 2 plus 1, which is equal to 6. So my ordered pair is going to be -1, 6. I have my point and I have my slope. I'm going to label my x coordinate and my y coordinate of my point as x sub 1 and my y sub 1. I'm going to write down point slope form. Y minus y sub 1 equals m times the quantity x minus x sub 1. And I'm going to substitute everything I know into it. So I'm going to have y minus 6 equals -8 times the quantity x minus a -1. So I get y minus 6 equals -8 times the quantity x plus 1, and I'm going to go ahead and just box that in. I'm going to leave that in point slope form. E. Determine the value or values of x for which the function would have a horizontal tangent line. I'm going to highlight the words a horizontal tangent line. At a horizontal tangent line, the slope is going to be equal to 0. I'm going to also underline the words a horizontal tangent line and draw an arrow underneath, and I'm going to write down slope equals 0. And then I'm going to write down f prime of x equals 0 because that's what we said the derivative represents. The derivative represents the slope of the tangent line. Now that we have written that down, I'm going to write f prime of x equals 6x minus 2, and now I'm going to set this derivative equal to 0. I'm going to put a cloud around the f prime of x part and draw an arrow underneath pointing to, and I'm going to write 0 right underneath it and set that 0 equal to 6x minus 2 and solve for x. I'm going to add 2 to both sides, and then I'm going to have 2 equals 6x. I'm going to divide by 6 to both sides, and I'm going to have x is equal to 2, 6, and that means x is equal to 2, 6, which I can divide by the greatest common factor of 2 to numerator and denominator, and that'll leave me x is equal to 1/3. So that's going to be my x value for which the function is going to have a horizontal tangent line. So I'm going to write out here in words, when x equals 1/3, we will have a horizontal tangent line. I'm going to box that in. That's going to be our answer. So now we are ready to move on to our next topic. Our next topic is going to be on differentiability. There are certain cases where the derivative of a function does not exist. In those cases, we say the function is not differentiable at that point. Let's look at some cases. A function is not differentiable at any point x equal to c if it is not continuous at that x value. So for this next example, f of x equals 1 over x minus 2. Notice I've highlighted the denominator x minus 2. I've drawn a cloud around it. I've drawn an arrow pointing toward the right. And I've written out the equation x minus 2 equals 0. I've added 2 to both sides, and I've gotten x equal to 2. At this value, the function is undefined. We also know that that means that at this value, there is a vertical asymptote occurring at this function. So I'm going to go ahead and draw a picture. Here is a coordinate plane. I'm going to draw at x equal to 2 a vertical asymptote. So I'm labeling some of the tick marks here on the x-axis. I went from 1 to 3, so I went from 0 to 3 on the x-axis by a scale of 1, and I've labeled my x-axis with an x, and my y-axis I labeled that with an f of x. So right on top of where x is equal to 2, I'm going to draw a dashed vertical line. And I'm going to label that line with the equation x equal to 2. I'm going to go ahead and draw a sketch of the function f of x equals 1 over x minus 2. So I have gone ahead and drawn a curve on the right-hand side of my dashed line above the x-axis that is decreasing, and it is concave up. And I have drawn a curve on the left-hand side of the dashed line that is below the x-axis. It is decreasing and it is concave down. So if f of x is not continuous at x equal to 2, then f prime of 2 does not exist. I'm going to box that in. Theorem. If f is differentiable at a, then it is continuous at a. Stated equivalently, if f is not continuous at x equal to a, then f is not differentiable at x equal to a. In parentheses, I'm going to write f prime of a does not exist. So here for our second example, the curve becomes vertical at that x value. And the example here is f of x equals x raised to the 1/3 power, which is also equivalent to f of x equals the cube root of x. I'm going to draw a coordinate plane here, and I'm going to draw a sketch of this function. The curve starts in quadrant 3, and it looks like it's increasing and it's concave up. And then when it gets to the origin, at x equal to 0, the curve becomes concave down. Even though it is still increasing, now it is concave down, and it is in quadrant 1. So I've gone ahead and labeled my function f of x equals x raised to the 1/3 power. I have drawn a little red dot at x equal to 0 with an arrow pointing at it, and I have written there next to that value of x, at x equal to 0, there is a vertical tangent line, and the slope of a vertical line is undefined. I have drawn a dashed vertical line right on top of the y-axis at x equal to 0 to show where this function has a vertical tangent line. Now I'm writing on the left-hand side of the screen, at x equal to 0, the curve becomes vertical so f prime of 0 does not exist. And I'm going to go ahead and box that in. Our third example, number 3, the curve has a sharp point at that x value. And in parentheses, it says there are different derivatives from the right and left. Example, f of x equals the absolute value of x plus 1, and then outside the absolute value we have plus 2. I'm going to draw a coordinate plane on the right-hand side of the screen. I'm going to go ahead and draw a sketch of this graph. First, let me draw some tick marks on the y-axis. So I drew tick marks from 0 to 3 by a scale of 1. And I've labeled those tick marks 1, 2, 3. And then I've also drawn tick marks on the x-axis from 0 to -3. And I've labeled in -1, -2, -3 for those tick marks. I've labeled the y-axis with f of x, and I've labeled the x-axis with x. I'm going to draw a table of values on the right-hand side of the screen. So in the first column I have values of x, in the second column I have values for f of x. And for x I have written in the values -2, -1, and 0. So it's going to be the ordered pair -2, 3, -1, 2, and 0, 3. So I've gone ahead and drawn these 3 points in. I'm going to connect these here so it looks like a V, with the vertex of this function being at -1, 2, and this function opens upward. There is a sharp point occurring at that ordered pair -1, 2, or where x is equal to -1. I'm going to go ahead and write in here on the left-hand side of the screen, f of x is not differentiable at x equal to -1. I'm going to box that in. Now let's move on to our next topic. Here, a function is differentiable at a point if it has local linearity. So a function is locally linear if and only if that interval is sufficiently small for a tangent line to closely approximate the function over the interval. So I've drawn a curve here to represent a function. I have drawn a tangent line at this point. And I have also drawn a rectangular box surrounding the area where the line is tangent to the curve, and I've highlighted the area. If we look in here, like we zoom in very close in, it does look like this line could approximate this function, this curve over that interval.